Hello, my name is David Sims. I'm a graduate student at California State University, Long Beach, and my major is Geographic Information Science. In the first video of this three-part series, I demonstrated how to use Python tools which I developed. These tools help you use slope, derived from a digital elevation model, to improve classification of Landsat imagery. In the second video, I explained how the Python scripts work. In this third and final video, I would like to talk about some possibilities for future research. So, after slope has been applied to the classified image on this side, this is the result. But we still have some work that can be done. And that is because we have pixels that are misclassified as shadow. And you can particularly see that here where we have granite mountains, and then on the back side of each one of these you'll see the little dark colored streak classified as volcanic mountains. This is shadow, and this is happening here, right there, and also on the back sides of these mountains, but it doesn't stand out as much because there's so much volcanic mountains mixed in with this with granitics here. So the way I propose to resolve this issue is to use a combination of aspect, slope, the class here, and con statements in spatial analysts. So the method I developed in the first video, that could have been done using the con statements, and that would work for some of the classes. So the two conditions would be the slope and whatever the class was on this side. And then you would basically say, when these two conditions are met, reassign a new value. We could have avoided generating 40 files, having to assign new values to them, and so forth. But the thing is we had really bad classification with unsupervised classification. Like, we had shadow and volcanic mountains mixed with granitic alluvial fans. It was a total mess. And so we needed to actually visualize each file so we could determine what the output class would be. But in this case, we can use con because we already know what the output class is going to be. It's going to be shadow. And we already know what the criteria are for their input. Therefore, con works really well. It's when you're unsure what those classes are that you need to do it as I did in the method to create this. So what I propose is making a Python tool which basically help the user write the con statement. And in this example, it could be possibly very easy. Anywhere you have granitic mountain and an aspect of whatever you determine after you do a little investigation, you create a aspect file, and then you lay it over this and get the pixel values where we're having the occurrence of shadow. And maybe it would be that simple. But you see here that we don't see any shadows here. This could be that there's just no values right here, or maybe they're very small and the pixels are failing to draw at this scale. But maybe the slope needs to be something greater than 30%. So we could maybe add something to it, like another criteria. We use the DEM again with slope, and maybe that's a third criterion. And then you could maybe get rid of the mountain class. Instead, you would say just use slope, and you'd be like maybe everything 45% slope or greater, and an aspect of such and such is going to become shadow. So that's one direction we could go to improve the classification of imagery. Another idea I had was that we could use elevation And it's only going to be, useful in some study areas. Here, there's only a little bit of vertical relief, and it's not really going to be that helpful. But in other areas, it could be really helpful, and the tool could just be slightly modified. You just sort of replace the slope tool with elevation, and you get user inputs for 4 elevation classes, and then you could apply that to your image to reclassify and pretty much reuse the same tool. And so the way this will work is it could be applied in areas with strong altitudinal zonation, and think of the east slope of the high Sierras, for example. And also think maybe our classification was using NDVI. So now we're going to have areas that are like medium and high biomass. Down in the Owens Valley at 3,000–4,000 feet, high biomass is pretty much only going to occur along streams in riparian habitat. And so you could maybe isolate that with elevation class 1, 3,000 to 4,500 feet or something like that. And then instead of calling it high biomass, we could now say it's riparian habitat. We're also going to get the medium and high biomass at a little higher elevation, maybe 4,500 or 5,000 feet to say 7,000 feet. And here you're going to have pinyon and juniper forest. And so anywhere that you're getting medium or high biomass, you'd have to kind of feel it out, but anywhere that's happening, you could now say this is pinyon and juniper forest. Again, from 7,000 to 8,000 or 9,000, now you would have subalpine forest. And finally, you would end up with alpine at the highest elevations. And then if you do a little bit of research, you might even be able to get a better classification. Rather than just saying subalpine forest, well, you could do some research. Subalpine forest in the high Sierras consist of primarily these species of trees, maybe white pine or Jeffrey pine or Douglas fir. And now you could start breaking out species possibly, or you could say these species are going to occur there. And so that's another way you could use a DEM to help add ancillary data to your classification method and get some improvement there. And I think that'd be something very easy to do and really could just modify the tool that I've already created. And so I hope to pursue these at a later time, and I hope you've enjoyed this little video. I know I have. Thank you for watching.